This video is going to talk about the geometric interpretation of a linear programming solution and also talk about the sensitivity reports that come along in the Excel output. Let's take a look at another problem. So let's just call this the table example, and it's a little bit simpler than the other examples we've been looking at in that there's only two constraints. Okay, so let's say we have a company that makes two types of tables, and each type of table is going to take two types of woods. Okay, so we're going to call these table 1 and table 2. So this could be, I guess, a dining room table and a living room table, something like that. Now, if we make a table 1, it's going to take 2 units of wood number 1 and 1 unit of wood number 2. Now, if we make a table of type 2, we're going to use 1 unit of wood 1 and 3 units of wood 2. For now, let's just assume that we make $10 profit for every table 1 we make, and $14 profit for every table 2 we make, and that we have a total of 10 units of each wood in our warehouse. So the question is, how many of each of these two types of tables should we be making so as to maximize profit? Okay, so let's go set this up in Excel. I'm going to get out of Word here for a second. And I've set this up. So here's the profit per table. The decision variables are up here. So I'll just say right now we're going to make 0 of each. And then let's take a quick look at this formula. The formula, I'll use sum product, $3, $3, which means we're going to hold the decision variables constant. We're going to multiply that by B4, C4, and then add that up. Okay, so let's just check and see how this works. If I made 1 of table 1, my profit should be 10. Okay, cool. If I made 2 of table 2, well, 2 times 14 is 28, plus the 10 should get me up to 38. And sure enough, that's the case. All right, so I think I set that up right. Now let's look at our constraints. I've got 2 types of woods that are used in producing these tables, and I use 1 unit of wood 1 to make a table 1. All right, sorry, I use 2 units of that and 1 unit of the second. Let's start that over. I use 2 units of wood 1 to make a table 1. I use 1 unit of wood 1 to make a table 2. And then you'll see the same sum product works. So this is going to be the total amount of wood 1 that I used. Where does 4 come from? Well, 1 times 2 is 2, plus 2 times 1 is 2. It gives me a total of 4. All right, now remember I have 7 available, so if I were to make 1 and 2, I've not really used everything. I've not used all the raw materials, so I should be making a bit more than that. All right, let's go use Solver. So I'm going to go into Tools, Solver, and you'll see that I've already set this up, but let's just walk through everything. My objective is to is specified here in D4, and I want to maximize that. So we want to maximize our profit. Now, how do I do that? Well, I do that by changing my decision variables. My decision variables are specified here, B3 through C3. That's the number of tables that I produce of each type. And then I've got one set of constraints. The constraints here are that the total amount of each of these woods that I use must be less than or equal to the amount that's available, which is 10. Now, really, there's another set of constraints, which is that I can't make a negative number of tables. The other thing that we want to do is to be sure to set this to the simplex linear programming method, not the nonlinear programming method, which is the default. So I'm going to change that to simplex, then I'll go hit solve. And so Excel's going to take a couple seconds to think. Now we get our results, and it looks like we have found a solution. The only thing that we really want to do here is be sure to check off sensitivity. This is going to give us some reports that we're going to interpret. So go hit OK. And what you'll see is that we now have a new tab called Sensitivity Report 1, and let's make it a little bit bigger, so we'll double the size. We get two parts of this. So one is going to tell us about the effects of changing the profit per table. So we'll talk about this in a second. The other one's going to talk about what happens if we were to get more or less of each of the ingredients, wood 1 and wood 2, available. How would that change our profit? Okay, well, we'll come back to that in a second. Let's go back to the PowerPoint. Actually, before I do that, let's go back to the solution. So the solution is as follows. We should make 4 table 1s. We should make 2 of table 2. Now, if we do that, we'll make 4 times 10, which is 40, plus 2 times 14, which is 68, total profit. How did we do on our resources? Well, it looks like we used every last bit of resources. So we had 10 of wood 1, we used all 10. We had 10 of a wood 2, we used all 10 of that as well. All right, so remember, we're using 4 of wood 1, we're making 4 of table 1, 2 of table 2, and our total profit is 68. So let's go back to the Excel for a second, or PowerPoint. And here I've just stated formally what we did in Excel, our objective function, our constraints. Now let's think about what these constraints mean. Now x1 and x2 are have to be positive, and then we've got some lines that we have to be less than. All right, so let's think about the constraints. I'm gonna draw this on the x1, x2 plane. Now the fact that x1 must be positive, okay, we have some lines coming in. I'll explain this in a second. What this means is that the x1 values that are feasible are all positive. Now all the x2 values must be positive, and what that means is that our tables, the number of tables made has to be non-negative. Now we have some constraints. The first constraint was on wood 1. Okay, so that was this equation right here. The constraint on wood number 1. And I think we're going to get that line in a second. So whatever combination of x1 and x2 that we make must be less than or equal to the amount available. So that's what this line does. All right, so if we made 0 units of x1, then we have at most 10 of this, because we use 1 unit of wood 1 for every table we make. Whereas if we made 0 of x2, remember using 2 wood 1s to make a table 1, the most we could make is 5. Okay, so that first constraint, the wood 1 constraint, is this line. And so that's saying we have to be to the left of this line. Now the wood 2 constraint is specified by this line. We're using 3 units of wood 2 to make a table 2. We're using 1 unit of wood 2 to make table 1. So that's this line. We have to be below that line. So the intersection of these 4 constraints, so the 4 constraints being x1 greater than 0, x2 greater than 0, the wood 1 constraint, the wood 2 constraint. So the intersection of all of those 4 constraints gives us this shaded region. That shaded region is called the feasible region. So what this means is that any point in this shaded region is feasible. As soon as we go outside of this region in any direction, we violate one of those constraints, and it's just not possible. So in other words, if we went up here, we'd be using too much wood 2. We don't have enough wood 2 to make a solution up here. If we went out in this region, we'd be using too much wood 1, and that would be a problem, because we only have a finite amount of this stuff. If I went down here, of course, I'm making a negative number of table 2s. That's not possible. Here a negative number of table 1s, that's not possible. Negative both. Here I would exceed my constraint on both would 1 and would 2. All right, so any value in here is feasible. Now let's think about the objective function. The objective function is going to, it was as follows. I make 10 profit for each x1. I make 14 profit for each x2. And when I fill in my x1 and x2, I get some profit. So we can think of the profit as like the constant in a line. Now we could, if we want the usual slope-intercept form of that line, we could move this over to the other side, divide by 14, and then 68 divide by 14 would be our intercept for this particular solution. All right. So the point I'm trying to make with this is this objective function has a specific slope, and this slope is going to be minus. We move this over to the other side, minus 10 over 14. Okay, so this objective function is specifying, a line with slope minus 10/14. So these lines all have slope minus 10/14. And then the intercept is going to be, well, profit divided by 14. Right, would be the quote y-intercept or x2 intercept in this problem. All right, so what we want to do is find the largest, the most extreme line that is still feasible. And so, any point on this line would be feasible, but we're not really maximizing our profit. Well, if we go out further, we're making more profit, but we haven't quite pushed it as far as we could. When we go out to this solution, we've now reached the boundary of our feasible set, and we're going to make our profit as large as possible by manufacturing 4 of table 1, 2 of table 2, and that gives rise to a total profit of 68. So note 4 times 10 is 40, plus 2 times 14 is 28, giving us a total of 68. So there is no other combination of table, x1 and x2 that would give me more profit than that. All right, good. So that's the geometric interpretation of this. Now let's take a look at these sensitivity reports. I've copied them into Excel here, or into PowerPoint. We have 2 sets of these. Let's take a look at the top one and interpret this. So the profit for table 2, I'm just going to interpret table 2. The interpretation for table 1 would be the same, about the same. So let me ask a question. Suppose that I changed the profit that was that I would obtain from table 2. So maybe I make more money on table 2 for each table 2 that I made, or maybe I make less money. So if that profit number were to change, what would happen to the solution? All right, the answer to that question is in this table. So the allowable increase is 16, the allowable decrease is 9. Now, what does that mean? What that means is that I could increase the profit that I make on table 2 up to $16. So if it went up to, if I made $15 instead of $14, this solution would not change. If I went up to, $25, keeping $10 constant, I would still make 4 of 1 and 2 of 2. It's not going to change until I get up to a profit of 30. So 14 plus 16 is 30. At that point, my final solution would change, and since the profit of table 2 is so high, so if I made it something like $31, you could almost guess what the optimal solution is going to be. It's going to be, well, stop making table 1 because you make so much money on table 2. Use all your available resources to make those table 2s since they are so profitable. All right. So that's what the allowable increase means. So up until a profit of 30, this solution doesn't change. Now, what does the allowable decrease mean? Well, this is the amount I could decrease this. So if I take 14 minus 9, so that's equal to 5. Up until a profit of only 5 on table 2, this would not change. Below 5, so let's just say it were 4, you can almost guess what the solution is going to be. The solution would be, don't bother making table 2 because it's just not profitable. Put all your wood into table 1. All right, so let's see how this works out graphically. So what happens when I change this coefficient 14? So if we change this this coefficient, for the profit on table 2, geometrically it's going to change the slope. Okay, so here was the original line representing the objective function. Now let's think about what happens if I change this x2 coefficient. Okay, so if I change that x2 coefficient, the slope is going to change. So if I changed my objective function to something like 10x1 plus 30x2, so now all of a sudden I'm making a lot more profit on table 2. Well then, I like to think in terms of basic slopes and intercepts. So to get there, I guess I'd move the 10x to the other side, and I'd divide by 30. Okay, so notice by dividing by 30, I'm dividing by a bigger number. Earlier I was dividing by 14. So when I divide by a bigger number, what that means is this profit function is going to get flatter. Okay, now as soon as I hit 30, what do I get? 10x1 plus 30x2. Well, that looks a whole lot like this other constraint, doesn't it? Okay, so in other words, my profit function is going to be parallel to the wood 2 constraint. So 10x1 plus 30x2 is parallel to x1 plus 3x2 equals 10. Okay, so my new profit function is going to be parallel to this. And what's going to happen with this exact profit function is that it's going to sit right on top of this constraint. And so, at a profit of 30, so 10 for table 1, 30 for table 2, any point on this line is on the boundary of the feasible set. And anything there works. Now what happens if we exceed the value of 30? Well, then the line gets slightly flatter, okay, and all of a sudden this becomes the optimal solution. So we're going to move to a different corner of the feasible solution. And what does this say? It says, don't manufacture any table 1s, put everything you've got into table 2, and that's going to be what maximizes your profit. So our intuition corresponds with what the geometry tells us. Now let's think about the effect of decreasing the profit on table 2. So if I decrease it to 9, what happens? Well, now my objective function is 10x1 plus 5x2. Well, that is going to be parallel to the constraint on wood number 1, which was this one. Okay, so if I decrease my profit, this profit function gets steeper, and the only thing that's going to be feasible is any point on this line. Now, as soon as I go below a profit of 5, what happens? Well, then the line gets slightly steeper, and this corner of the feasible region becomes the optimal solution. In other words, don't make any table 2, so make 0 table 2, put everything you've got into table 1 to maximize profit. All right, so I hope that that's clear. And now let's just go back and interpret the one for table 1. Okay, so if we hold profit constant for table 2, I'm going to keep this solution up until I'm making, if I made up to $28 per table 1, this thing wouldn't change. Likewise, if it decreased to about 4.6 something profit on table 1, the objective function wouldn't change. However, if I make more than 28, so 10 plus 18 is 28, so for example, if I made $29 per table 1, the solution would change to put everything into table 1, don't make any table 2. Likewise, if the profit on table 1 decreases below about, decreases to about 4, then I'm not going to make any table 1s anymore. I'll just put it all into table 2. So that's what sensitivity means. It just means, how sensitive is this solution to these profit coefficients? Often we don't quite know what these profits will be if we're a price taker. These might just be our best guess. In this case, this final solution, the optimal solution, holds across a pretty wide range of profit values. So in other words, this isn't going to change unless the profit per table changes by quite a bit. This is just giving us a window where we think, where the solution holds. All right, let's move on to the other part of the sensitivity report. So down here we have some additional constraints. We have these shadow prices. So what do the shadow prices tell us? Well, they tell us something about if we had a change in the availability of wood number 1. So in other words, if I could get some more wood number 1, well, then I could make more tables, right? Well, what would that be worth to me? So let's interpret the shadow price for wood number 1, which is 3.2. So this is saying if I could buy an additional unit of wood number 1, then my profit would increase by 3.2. Now this is true within a range of, well, the allowable decrease is down to 0, the allowable increase is up to 16.6666. Beyond that, the story changes. All right. Likewise, if I wanted to sell some of my wood, maybe I don't want to make tables anymore. I've got all this wood sitting around. I could sell it on the market. And what's that going to cost me if I have one less of it? Well, my profit would go down by 3.2. All right, so let's go look at the geometry of this. So what does it mean then to get more of wood number 1? Well, what it means is that I'm going to shift my constraint. So this was the original constraint. 2 times x1 plus x2 is equal to 10. Now the constraint was actually that it had to be less than or equal to 10, which gave us this feasible region. Okay, now if I had more of wood 1, then that 10, would become an 11. Okay, so then this whole line would shift. The ratio, the amount that I use to make table 1 and table 2 doesn't change, but the line shifts out. Likewise, if I were to sell some of my wood number 1 on the market, then that would mean I'd have to make fewer. This whole thing would come in, but it would shift in a parallel way. All right, now where do these numbers, the allowable increase and the allowable decrease, come from? So given that by changing my supply of wood 1, all I'm doing is I'm moving this constraint around, All right, what happens if I increase this? So originally I had 10. Let's go out to add another 10. So if I had 20 units of wood 1, well, what does that line look like? Well, notice at this point, I run into a new boundary. So this is a new boundary that, here's the wood 2 constraint and the non-negativity constraint. At the value 20, those three constraints all intersect. All right, and so then, beyond this, beyond having 10 units of wood 1, my solution isn't going to change anymore because I've run out of wood 2, right? And I run into yet another constraint, and that is this wood 2 constraint. So it doesn't help me to go beyond 10 because at that point I need to get wood 2. What about the allowable decrease now? All right, so with the allowable decrease, remember this line's going to start moving towards the origin as we decrease the amount of wood that we have available. Now, the change in the profit function is going to change at a constant rate. We're just moving along this line until we hit this value. So we can work through that value. It's 10 minus this. And this is where, again, we have three constraints matching up. Now, if we have less wood than this, then all of a sudden we start following a different constraint, which is this non-negative constraint. So if we get really low on wood number 1, for example, if we were in this region, then, well, we're going to make 0 table 1 and 2 of table 2. But the point is, the shadow price, the rate at which our profits change, will be a little bit different when we're moving down this constraint as opposed to moving on this constraint. Okay, so that's the interpretation of the allowable decrease in the shadow prices. I encourage you to think through the interpretation of the sensitivity report for the golf bag problem now.